Hello, this is Tyler Abbott for Comp 340 Online 2, where in this presentation I'll be discussing chapters 8.24 and 8.25, covering remote procedural calls and distributed shared memory respectively. First, let's discuss remote procedural calls. What is a remote procedural call? A remote procedural call, or RPC, in the simplest form, is a remote procedure that is made to look as if it were local. The way this works is that the client program makes a call to the client stub, which is a library representing the server procedures on the client side. The server will have a near identical architecture where it will have a server stub, which represents the client procedures on the server side. These stubs work together in hiding that these calls are actually not happening locally, rather they're happening remotely. Now let's discuss the good and the bad of RPCs. First, the bad. The problem with RPCs is that it is not possible to pass pointers, since they're not actually using the same addresses. There are some ways to circumvent this, but they can be rather janky and ill-fitting, especially depending on the type of data structure being used. Secondly is global variables. Since these are separate machines and potentially separate code bases, they're not sharing the same global variables, which could be problematic. And the good is that the bad isn't that bad. We can get around these problems in some cases, and there's actually a ton of use cases. One of which could be distributed computing. Another could be a method of implementing multiplayer features in a game made in a game creation software like Unity. An RPC is just one of the methods one could implement an API or application programming interface into their software to get two devices to, in a sense, talk to each other. I wanted to learn more about practical examples of RPCs, so I took to the internet, and according to w3.com, which I believe to be a reputable source, after all their good notes on HTML and web development, makes note on their site of the potential use cases for RPCs, and they list things such as remote file access, remote graphics, and software management to stop, start, and control. Very interesting stuff. Next, we have distributed shared memory. This is the illusion of getting a distributed system to share memory. In this model, we are sharing memory at the operating system level in comparison to sharing at the hardware level or the user level. What happens in a DSM system, or distributed shared memory system, is that the entire DSM architecture divides all the available address space into chunks, or pieces known as pages. These pages are spread across all the involved machines. Simply enough, if a CPU is searching for an address that is realized to not be local to itself, a trap will take place and a fetch operation will then take place. Once found, the CPU holding this page will be asked to unmap it, then send it over to the CPU looking for it, and it will be mapped after successfully receiving it. This is the illusion of shared memory. In the example shared by the text on the right-hand side, we can see visually that each CPU owns a subset of the total pages available across several CPUs. In this short demonstration, we can see that CPU 0 is gaining page 10 and CPU 1 loses page 10, inferring that CPU 0 was searching for page 10, realized it was not available locally, and performed a fetch operation from the current owner, and thereby unmapping it, sent it over the network, remapped it, and then finally restarted from the faulted instruction. Next, let's discuss false sharing. This problem arises in the DSM space because of the aforementioned unit of measurement known as page. Each page is a chunk of memory that can contain several variables or other data. if there's a subset of data that CPU1 requires and a subset of data that CPU2 requires, where both of these subsets exist on the same page, CPU1 and CPU2 will be constantly sending this page back and forth over and over each time one makes a request to use the page again. The way we can potentially mitigate this problem is by making each memory chunk, known as page, smaller. Inversely, the bigger the chunk, the more susceptible the system is to false sharing. And on this slide, I included a picture of Biggie Smalls because bigger chunks, bigger problems. I hope someone gets that joke. Next, we have replication and achieving sequential consistency. Replication is a simple modification to previously mentioned architecture, where we can replicate read-only pages to other CPUs, thus not having to share the chunk of memory. We could even share read-write chunks, so long as there are no changes done to the chunk, creating a difference between or discrepancy between those two chunks. We'd have to ensure that both copies remain the same at all times if modifications are to be made. This then rolls over to the conversation about achieving sequential consistency. What we could do to ensure all replications of a chunk of data is consistent across several CPUs is to destroy all other copies where a modification is made to one of the chunks. If a modification is about to be made to one of the pages, we would first write to the bus line and tell the other CPUs to destroy their copy. Once this has been completed successfully, we can then write to our chunk and we can move forward as business as usual, and this chunk can be replicated once again if need be across two of the other CPUs. We could also consider an alternative method, such as locking mechanisms, where we can lock a piece of memory to read and write to, then upon completion we push the changes we made to this memory block to all other replicas, thus mirroring and retaining consistency. After stumbling across a presentation performed at Columbia University in New York regarding types of consistency, they note that there are other types of consistency, notably causal consistency and eventual consistency. Simply speaking, eventual consistency focuses on data availability and will eventually update all other data to mirror one another. It's an optimistic model that may or may not always be consistent, but it's always available. Causal consistency is where each individual process observes the read and write operations in their own requested order. And items that are not causally dependent can be executed in different orders. This method is actually weaker than sequential consistency, but stronger than eventual consistency. And in the industry, it does not seem to be a very popular model, despite it actually being faster than sequential. Eventual consistency actually does see some industry standard. Thank you for watching.